Welcome to this course on two-dimensional signal processing, principles and practices. We have done the Z-transform for two-dimensional sequences and inverse Z-transform as well. Also the solution of the linear constant coefficients difference equations for 2D, in which we have found the LSI system, what are the conditions to be set for the LSI systems. So those things would be useful in the case of filter designs and then filter transfer function representation and know the filter response. So if we take the filters design and the digital filters, especially the design, we have the two flavors in it. One is the finite impulse response digital filter and the infinite impulse response digital filter. So for the sequence which is having the 1D, in the 1D case, you can have the certain values of n, you have the amplitude, the sequence is plotted over here. So if you give this sequence to the filter, which has some specification, it can be a low pass filter, or the high pass filter, or it can be an all pass, or it can be a band pass or band reject. Some frequency components are to be preserved at the output, and a band of frequencies can be removed from the input. So that's how the output, which is over here noisy, is getting the output response. So whereas in this, the low frequency content is preserved and the high frequency content, which is a noise, removed from it. So this digital filter design. So how do we do this filter design in case of 2D is this week course. But before getting into the 2D filter design, that we will know the basics of this 1D digital filter, especially the finite impulse response filter, and then we'll move on to this infinite impulse response filter designs. So this digital filter is going to be a software program, or it can be a processor in which the program can be dumped to it. In case of it can be a DSP or an FPGA, it's going to be an integrated circuit when we mean digital filter. So this digital filter, it can be two types like FIR and IIR. This week we'll take FIR for the design, and then we'll move on to the IIR filters. So the FIR filter, the finite impulse response, the name itself implies that impulse response has finite extent support. In that case, that current and past input samples only it takes and gives the output, that is the deciding the current sample output. The current output sample is based on only the current and past input samples, and no past output samples are required to decide this current output sample. So that's the thing to be noted. So x of n minus 1 and any past input samples can be used to decide this current output sample. And the moreover, the impulse response, the finite duration non-zero input samples. So if we apply, then output would also be of finite duration non-zero output sample. So this is finite, and here also finite, and moreover this is non-zero, and we get this also non-zero. So if input samples are suddenly become 0, so if we apply the input and then make the input 0, then output will also come to 0 immediately. So in the case of finite impulse response, because it doesn't store any values of the past output, it doesn't need that. So the input depends on this present input, the output goes to 0. And this is a non-recursive filter because it is having only the past inputs and the present input. And case of IIR, just to not very exhaustive comparison, just a hint of this IIR filter. Then when we do the IIR filter, we'll do the discussions more. So the current and past input samples, also it takes the past output samples to decide the current output sample. So this was not the case in the FIR. And here if you give these samples like the impulse response, infinite duration 0 output samples. So if you apply the input and then make it 0 suddenly, and the output will not become 0 in this case of IIR, because it has the feedback circuits as well. So the past output samples are given to the input here, and then the current output sample is decided. So this will have the infinite duration non-zero output samples, and if you make the input suddenly 0, then that won't reflect in the output immediately, then making the output sample 0. So there will be a feedback and oscillations and so on. So that we would study in the case of later. So it's a recursive filter, and that FIR is a non-recursive filter. So taking just to introduce this FIR filter equations, that's y of n, the output is having the b naught, the coefficients, b naught x of n plus b1 x n minus 1 and b n minus n x of n minus n minus 1. So this decides the order of the filter, that n. And if we take the z transform, as we know this for 1D case, y of z by x of z, so it gives only the coefficient in terms of this z bar minus 1 and z bar n minus 1. So for an FIR filter, if the input is applied as impulse and the output is going to be an impulse response, for this impulse response, if h of n is known, and we know that for an LSI systems that you can find the response of the system for any input, any arbitrary input, by knowing the impulse response, convolving that we can get the y. So the x and convolve with h, will be y. So here this h of z, which is the transfer function of this FIR filter as well, is obtained from n equal to 0 to infinity h of n z minus. So this is the z transform, and if we compare these two, this h of n is equal to here b naught b1 b of n minus 1. So these are the coefficients. So if we apply the input here, the convolution of del of n, and in with the filter coefficients, so the impulse convolution of this impulse input and the filter coefficients results in impulse response, that is nothing but filter coefficient itself. So that's why this, it is called the impulse response have this having the filter coefficient itself. So deciding the filter coefficients, or for the given specification, finding the filter coefficients is nothing but the filter design. Now the FIR filters are linear phase filters because the coefficients can be of in these 4 types. That is, we can have the coefficients as midpoint symmetric and midpoint antisymmetric, 2 categories, and the number of coefficients, is it even or odd, depending on that, it is midpoint or midpoint symmetric or midpoint antisymmetric, we can classify them as 4 types. So the type 1 will have this odd length coefficient. Here we can see this from 0 to 6, there are 7 coefficients, the coefficient length is odd, and it is midpoint symmetric with respect to 3. These two coefficients are having the same value of h of n. So here you can see that this is midpoint symmetric and with respect to 3 and odd length. So that's type 1. And if we take the type 2, that's for the even length, from the coefficient 0 to 6, instead of that 0 to 5 we have so these are there are 6 coefficients here, which is symmetric about here 2.5. It's not 2 or it's not 3. So it is this is symmetric about this 2.5. So this is called midpoint symmetric, but this is of even length. Okay, so type 2 filter. And type 3 having this antisymmetric case, where where for the odd length 0 to 6 there are 7 coefficients here, and this one, and you can see the h of n having this amplitudes antisymmetric, this positive and this is negative, and here positive and negative, and so on. So this is antisymmetric case with odd length 0 to 6, that is 7 coefficient. Similarly here 6 coefficients are there, 0 to 5. So this is midpoint antisymmetric with respect to 2.5 again. So this is the type 4. So even length, okay. So even 2 and 4 and the odd length coefficients having this type 1 and 3. So these filter coefficients. So if you design a filter which is having this type of coefficients, like it would show the linear phase response. So linear phase response, FIR filter having the coefficients midpoint symmetric or midpoint antisymmetric cases. So FIR filter designs are vast. I mean, we can design it in 3 different ways, but the popular method is that windowing method, used for FIR filters. So need to know the details of the windows, so that the filter design, FIR filter design using windowing or windows can be understood. This will do it for 1D, and the same thing we can extend it for 2D also for the windowing concept. So we need to know the windows which are popular windows in the case of 1D, and that using that we can extend that windows to the 2D windows, where the classification is like separable windows and then circularly symmetric windows of 2D type windows. So we'll use this 2D type windows to design the 2D FIR filters in the coming lectures. So first, knowing the windows of this used for designing the FIR filters. So we need to truncate the data here, that if we truncate the data using the windows. That's the possibility. Then whether we use the sharp cutoff, sharply the windows which are used or having the transition sharp, or it is smoothed. So in the case of sharp truncation, straight truncation, the data, it causes the spectral leakage, that is, it's spreading, the spectral leakage happen. Also, this can be solved with this increasing the window length, but also we have to, increasing the window length causes a certain problem, and the tapering is one solution to have this leakage down. Tapering is the another solution, that is smoothening the window. Instead of having the straight windows, we can have the smoothened window. Also, the window length and the bandwidth of which is used, which we get by designing this window, will have the reciprocal nature. So we have to look at all these points if we use the window for FAR filter design. So for a simple rectangular window which has some LW with 0 to LW minus 1. So this is the number of samples used here. So the LW can be 9 or 8 or whatever the number of samples. We will use this 9 for rectangular window, and we will take one of the problem for designing the FAR filter using this 9. So I just specify this as 9, and this is the window function W of n, which is rectangular window. And if we take the Fourier transform of it, is here, this would give the rectangular function, results in a sinc function, and the sinc function, which is the magnitude, is taken here, not the phase response. This is the magnitude response, which gives all the values positive, and this is the length or the width of the main lobe, and we can have the side lobe here. So if we plot this with respect to the log scale here, this 20 log of W e over j omega, which gives this 0, you can see the first half of the 0 to omega is plotted over here, in which the rectangular windows, this is the 0 dB, and the first main lobe comes with the value of minus 13.3 dB. So the first lobe is that the difference is that minus 13.3 dB, and this varies, the first side lobe level varies depending on the smoothening of the window, that we would see the case. So here the roll off rate is here, this is slow, we can see. So the rectangular window, the spectrum decays very slowly with the frequency, and the first side lobe level is 13.3 dB below the peak for the first 0 dB peak one main lobe, and we can have this impulse response to be truncated using the window for low pass filter design. And what is when we use this truncation, it would introduce a ripple in the stop band, and it would also broaden the transition band. So what is the relation between the transition band and the window width, or also the ripples in the introduced in the stop band? So these details will dig out further. So here is this desirable window spectrum has narrow, it should have this main lobe and small side lobes. So that's the good thing, that have the which will have this narrow main lobe and the small side lobes, so that the transition width and the ripples on the stop band can be controlled over it. So if we have the ideal window of rectangular one, which should be of infinite length, so the infinite length cannot be used, so we have to truncate it for the finite duration and also avoid the spectral leakage as much as possible. So if we have the peak side lobe level, this is if we consider that, that is going to be fixed for the different windows. So rectangular window will have this 13.3, and the other types of window will have the different fixed values. So this cannot be changed, because choosing the window can different windows, hamming and other windows would cause this side lobe level to vary, and at the same time main lobe width would increase. So that's the case. We would explore what are the windows which has this, which can be used in the design, and what is the drawback, and what are the constraints to be used. So main lobe width it shrinks as the window length increases. We have seen in the 9 sample window there is a main lobe width. If we increase the number of samples on the window, then this main lobe width would shrink. So inversely proportional, and the side lobe characteristics will be depending on the It's based on the characteristics of the window, that is, it will have the lower and lower ripple in the side lobes as we smoothen the window. So, but main lobe width would increase. That's the property of this window. So we can see the different windows, rectangular windows. These are the standard expressions used for this window, and the main lobe width, rectangular window which has 4 pi by LW, and triangular or barlet window, the equation is this one. LW implies the number of samples in the window, 8 pi by LW, and Hanning window expression is this. It's a very standard known window, and Hamming as well, 8 pi and 8 pi by LW. Blackman, which has this 12 pi by LW, the main lobe width increases as we smoothen the window here, and the Kaiser one, which is a tunable window, the alpha varies. It depends on the Bessel function 0th order. So the alpha varies, and the roll-off rate also varies. So the roll-off rate is -20 here, and that means the decay rate here, -40 and this is quick decay here, the Hanning and Blackman windows. Also the peak side lobe level is -13.3. We have seen this is -26, still further down, and 31.5 and 42.7 and 58.1. So as we smoothen the window, the ripple side lobe level gets decreased. It will have the smaller ripple in the window response, the frequency response. So it varies with alpha in this case, that can be tunable, that Kaiser window. So this is just a review of this concepts of the window used in the FEOF filter. So now taking the rectangular window and the triangular window. So if you get the response W of e power j omega, Fourier transform of it, which has this blue has the main lobe width less, and the triangle one which has the main lobe width wider compared to this one. And if you see the side lobe levels of this, triangular window has the less side lobe level. So if this can be clearly seen by plotting it with the 20 log of W of e power j omega, that is in dB. So with omega here, so this is the rectangular window, blue one, and the wider main lobe can be seen as we taper the window. The smoothening windows increases the main lobe, but the reduction in side lobe levels can be seen. So this is the rectangular window, and the case of triangular window has the lesser side lobes. So the triangular. So this is valid for the other smoothening windows as well. So the rectangular and triangular windows and its spectrum has been shown over here. So the types of window, if we take a few which are used in the design, so the rectangular window, and then the case of Hanning, you can see this green one is the Hanning, and black one is this Hamming, and the Blackman window, which is also smoothening window, and Bartlett window is the triangular window. So corresponding frequency responses are shown over here. The main lobe width is increasing as we go in this way. So the Blackman window has the wider main lobe width, at the same time it has very small ripple in the side lobe level. So the rectangular window has the sharper main lobe width, but it has a more side lobe level. So this can be visualized even in the case of log dB, magnitude is plotted in dB. So the first side lobe level in the rectangular is -13.3, whereas in Hanning window it is -31.5 and 26.5 in the Bartlett triangular one, and Hamming has this -42.7 here, as 58.1 for Blackman. So you can see the ripple side lobe levels getting reduced as we smoothen the window. Also, if we look at the main lobe width, this is the smaller main lobe width, and these main lobe widths are more and more. Here it is little less than 0.2 pi, here is also, and you can see the main lobe width increases. This is more than in the Blackman, more than 0.2 pi here. So main lobe width increases. So tapering causes the main lobe width to increase and the side lobe level to decrease. So how do we use this in the filter design? So what are the steps involved in the filter design? So if you consider parallelly the time domain as well as the frequency domain details. So in the case of time domain, so these are the sets of procedure needs to be followed, and in the frequency domain equivalent it can be. So when we design a filter, first thing is the specifications are defined in the case of frequency domain. That means the desired frequency response needs to be known. HD of e power j omega, whether it is going to be a low pass filter or a a band pass filter or anything. Ideally, this is going to be, suppose taking a low pass filter, it's going to be a rectangular function. So the rectangular, if HD of e power j omega, the desired frequency response is rectangular function, then its Fourier transform, inverse Fourier transform, taking this in the time domain, will give the HD of n, that is the coefficients, that's going to be a sinc function. The ideal low pass filter will have the infinite number of coefficients in the filter, this HD of n, which is a sinc function. So this sinc function, so we cannot use this, the ideal filter design is not possible. So practically we cannot have the infinite number of coefficients, so we need to truncate it using the window function. So the window function is decided Wn, any one of the window which we had studied now, that one rectangular or the Hamming or Hanning window, and multiply this to HD of n and W of n, get the truncated coefficient. So this is just a multiplication of the two to get the H of n, that is the truncated filter coefficients. And what is happening equivalently in the frequency domain? So if we have this, if we once decide this window function and take the Fourier transform of it, that gives the frequency response of the window function, W of e power j omega. So if we multiply these two, we get the truncated coefficients, that's the design. But if we look at the frequency domain response of the response of the filter, where HD of e power j omega and W of e power j omega, these two are convolved to get the frequency response H of e power j omega. This is the actual response, this is the desired response. So this is the actual coefficient and this is the desired coefficient. So the infinite coefficients, to have it as the filter is not possible practically, so we need to truncate it using that. So we get this is what in the time domain, this is a multiplication, is nothing but the convolution in the frequency domain. So if we take the same thing here, so desired frequency response is, supposing I just draw it here, this is going to be this omega c and minus omega c cutoff frequency here, and the corresponding inverse Fourier. So if we take, that is going to be a sinc function which is having n infinite. So these are the coefficients which we get of HD of n, which spreads through minus infinity to plus infinity. But ideally this is not possible, that's what we had seen. So we choose a window that can be of rectangular window for some duration. This can be here and here. So here n, and this is, so take the Fourier transform of the window function. So the next one is here. So if it is a rectangular function, and this is going to be a sinc function. So this is omega. So here the rectangular function results in the sinc function, and the choose to truncate it, we choose the window function. It can be a rectangular or a smoothening window, Hanning or Hamming or Blackman, any kind of window. So it depends on the main lobe width and then side lobe level. So these have the impacts on the filter transition band. So that transition width, we can see the impact of this choosing this window function as well, and depends on the number of samples this main lobe width would be. And then in the next step, we'll multiply these two in the time domain and convolve these two to get the filter response. So here is truncated coefficients of the filter. You will suppose you have this, so we'll have up to a few points, 3. So here is 9 coefficients, depends on the number of coefficients in Wn. This is n, and the response, filter response H of e power j omega. For this, if we take these are the coefficients now we got by multiplying this Hd and W, and we get the filter response as this. So it will have a side lobe or the ripple, which is due to the side lobe level of the window function, and there is a ripple in the passband as well. So that is also, we will not be having the string magnitude response, ideal response as desired. So it depends on that number of coefficients. If we have the more number of coefficients, the order increases, and it will be the smoother and smoother the cutoff region, the transition region. So here is this passband frequency, this omega, and this is the stop band frequency. In between we have the cutoff frequency. So this we will see in the specification. So this is the actual filter which is to be designed here. This again, this is for the low pass case. So similarly, band pass and high pass thing can be done. So you can notice the convolution of the HDE of j omega, that is the ideal response, and the window function, Fourier transform of the window function. Convolve these to get the magnitude response of the frequency response of this filter. And there will be a phase response, obviously, the only magnitude response is shown, and also in the desirable case, so this is the magnitude response is shown over here. So this is the way in which the filter design is done. These are the few steps used in the filter design 1D using the window method. So now we see the filter specification. It's obvious, we know that this could be extended to 2D as well. So we have the pass band and the stop band. So we need to know what are the band of frequencies to be present in the output of this sequence, or what are the frequency content should be removed. So then this is h of e power j omega, that is the filter specification, or you can say this is desired, and we will have the ripple 1 plus delta p by 1 minus delta p. The amplitude of this ripple is decided by this delta p, and the stop band also we have delta s, the stop band ripple allowed. And you can see this WP, the pass band frequency, stop band frequency, and cutoff frequency. These are radiant frequencies. So these are the specification generally given. This is for the low pass filter case, for the filter design. So once we have this specification, and we will proceed with the window method for the FIR filter design. So taking an example here, so the desired frequency response, if we take e power minus j omega alpha between minus omega c to plus omega c. So the linear phase characteristics, as we have seen this FIR filter, midpoint characteristics offers the linear phase response. So which can be, the magnitude is 1 for the filter, and it's going to be, the angle is depending on the phase response is depending on the slope of omega alpha. So this is for the region of minus omega c to plus omega c, that is the cutoff. Other regions it is 0. So 1 minus delta p to 1 plus delta p is the ripple magnitudes allowed in the pass band, and the stop band is the ripple allowed. So these are the specifications of this ideal low pass filter. So for the linear phase FIR filter, the desired response of this filter HD of e power j omega, once it is given. So we said it can be it can give the HD of n, that is the coefficients can be decided. So the relation between this is just nothing but the Fourier DTFT. HD of n is the filter coefficient, and we can get the desired response. Once we know this, we can get the coefficients HD of n from the inverse Fourier DTFT. So 1 by inverse DTFT, 1 by 2 pi from minus pi to plus pi, knowing this filter characteristics and integrating with e to up to d omega, e power j omega and d omega. So if this is the ideal response, e power minus j omega alpha, so for the region of minus omega c to plus omega c, then we can integrate it. We can integrate and get the response of the HD of n. For a rectangular function, so this needs to be 1 for certain regions, certain length, n equal to 0 to n minus 1. As we had seen, that is going to be 9 samples, then 0 to 8. So this is a rectangular window equation, and the impulse response of this FIR filter, h of n, which is obtained by truncating the HD of n, the infinite coefficients by multiplying this Wn. So this h of n will be equal to HD of n for this duration of window function. So now getting into the frequency domain case, the window function for a rectangular window function, taking the DTFT. So this is W of n e power minus j omega n for the samples of length window, 9 samples, or n equal to here 9, 0 to 8 samples. So this can be some summation can be written like 1 minus e power minus j omega n by 1 minus e power minus j omega n. So where this is 1, so e power minus j omega whole power n. So this will give the finite sum 1 minus e power minus j omega, here n minus 1 plus 1, that is going to be resulting in n, and here 1 by 1 minus a. So that's a closed form solution when this is less than 1. So expanding it would give the sinc function as well as this. Taking the magnitude of it, which would give only, this is contributing to the phase, and this would give the magnitude. sine of omega n by 2 and sine omega 2 for the omega varying from minus pi to plus pi. So, the phase response is from here when this Wn by 2 is greater than or equal to 0 or less than 0, depends on that phase response will be. So, this is the window phase response. So, this is the response of the rectangular window function. So, frequency response of the window function is this. So, we need to get the actual filter response in the frequency domain, which is equal to hd of e power j omega convolving with this w of e power j omega. So, that would give the actual filter response. So, we will take an example of it and then see the design how it can be done for in this is 1D. So, we can extend again this insights to the 2D as well. For the case of low pass filter design, so this can be of high pass filter or for the given specification. So, low pass filter design, you use the rectangular window and 9 samples that we had taken the discussion to start with, it is 9. So, the window W of n has 9 samples, that means n equal to 9. So, 0 to 8 samples would be there in the W of n, and the cutoff frequency is 1.5 radians per second. This depends on the filter characteristics or what is the frequency need to be kept in the output or it should be removed. So, it depends on that, this can be fixed. So, for the case of 1.5 radians per second, let us see the low pass filter design. So, given the hd of e power j omega, the desired response is e power minus j omega alpha between the region of minus omega c to plus omega c, where omega is varying from this 0 otherwise. So, this response, if we visualize it here, where omega hd of e power j omega is 1 from minus omega c to plus omega c, that is 1, its magnitude is 1 and its phase is linear phase. We have the omega alpha slope, you can see the e power minus slope for omega. So, this is the angle of hd of e power j omega. So, this is the ideal response magnitude and its phase response. So, this is what is to be obtained using the sample of window having 9 and using the window of rectangular, and the cutoff frequency omega c should be 1.5 radians per second. So, how do we get the filter coefficients for it? So, knowing this hd of e power j omega, so get the hd of n, that is the infinite number of coefficients here, hd of n. So, by inverse dt of t, 1 by 2 pi minus pi to plus pi hd of e power j omega into e power j omega and d omega. So, where this is nothing but e power j omega l in this region minus omega c to plus omega c, and combine these two terms to get e power j omega and n minus alpha. Now, integrated with respect to omega, we get here hd of n as 1 by 2 pi e power minus j omega n minus alpha by j n minus alpha, that limits omega c and minus omega c. Apply it and get the expression as this 1 by pi n minus alpha. This 2j is combined with e power j n minus alpha and with the limits. So, it becomes sin omega c n minus alpha. So, this expression is valid for n is not equal to alpha. So, when n is equal to alpha, this hg of n becomes infinite. So, this becomes 0 and infinite. So, this is not valid, this expression, that is the the coefficient needs to be truncated, that is an infinite coefficient expression, that is a sinc function actually here. It is going to be the expression, but where n is not equal to alpha. For getting this expression for n equal to alpha, in that case use the L'Hospital's rule hd of n, limit n tending to 0 in this expression. We get differentiate it and apply this n equal to infinity and get this omega c by pi. This is the one for n equal to alpha. So, for n equal to alpha, this is omega c by pi, n not equal to alpha, this is the expression of the coefficient, not truncated one. So, that is a coefficient with from minus infinity to plus infinity. Now, we have to multiply this hd of n with the rectangular function, which has the coefficient 0 to 8. So, we multiply these two expressions. So, h of n will be equal to hd of n for n equal to 9. And n equal to 9, omega c is given in the expression, and find out alpha. Alpha is the relation between the n and alpha is n minus 1 by 2. So, 9 minus 1 is 4, alpha is 4. So, even if it is n is even, then it is simply n by 2, okay, in the case. So, the h of n what we got in the previous slide. So we go sine omega c n minus alpha by n. So alpha is known now and omega c cutoff frequency is given, and this is a truncated coefficient which is valid for n 0 to n minus 1, that is 0 to 8, where n is not equal to alpha, and n equal to alpha, the expression is omega c by pi. Okay, so use this expression and get the coefficients. Now for n equal to 0, we get minus 0.022, n equal to 1, and we get the sample as this, the coefficient from this. N equal to 2, this is 1, and n equal to 3 is okay, and not n equal to 4, we get omega c by pi. When n equal to 4, this is the expression omega c by pi. N equal to 5, 6, 7 and 8, these equation. So if we observe these coefficients, this is the designed filter or the filter coefficients obtained for the problem given. So h of 0 and h of 8 are having the same values, and h of 1 and h of 7, we can observe the linear phase characteristics, that is the midpoint symmetric, and h2 and h6 having the same values. Also the h3 and h5 will have the same values here, 0.3175, and this is with respect to h4, that is the midpoint symmetric, so which exhibits the linear phase characteristics of FIR. This is the example 1 using the rectangular window of 9 samples. So the case, similarly we can have this filter specification with ripples and so on, and involve the table which we had used. Okay, so that can also be used for, depends on the design of the delta P and delta S. Now giving the relation between this windows, main lobe and side lobe, transition width and so on. So if we suppose take this L is 20 samples, okay, the main lobe width of the case is this, and we said this L is increasing, number of samples increased, then the main lobe width decreases. Okay, so that is the case for L equal to 90, we can see very well here. So the window length increases, the main lobe width decreases. That's the point to be noted. One point, that is for L further maybe 20 or 50 or so on, so the main lobe width getting decreased. So if we use this window, so window which has L equal to 20, and if we design a low pass filter, so this is the transition width. If L equal to 90, the previous case, if you use that filter and you use that window and design a filter, in that case L equal to transition width getting decreased. So you can see the sharpness of this transition width. So as the window length increases, so the main lobe width decreases, and which has the main lobe width and the transition width has the direct proportional. So our increasing the window size decreases the main lobe width, also the narrows the transition band, which is good. So you should have the number of samples more in the window from this conclusion. But what about the ripples? Okay, so what about the window functions? So that maybe that is true for rectangular window. So if we take a rectangular window of n equal to 16 and design a filter, okay, so which has, this is the ideal one required. So the actual filter response what we get is the magnitude is this. So if we increase this n further, the transition width may improve, but there are ripples here, and that ripple, how do we use it? So if we have the smoother window like the Hanning window of same size n equal to 16, you can see the design which has the ripple wiped off. Here the ripple is reduced, and similarly here also. The ideal is this, and using the Hanning window, this ripple is gone, but you can see the transition width which is increased. That is due to the Hanning window has the wider main lobe compared to the rectangular window. So the main lobe width causes the transition impact on the transition band. So if we have the lesser main lobe, the transition width is sharper. We have the wider main lobe, the transition width is more. So we have in this case to increase this again to reduce the transition width, the main lobe width should be reduced. So for that n needs to be increased further. So if you consider this rectangular window, the Hanning window case, the transition width and the ripple, there is an advantage of ripple reduction, but the transition width has become more. So for the Hanning window of n equal to 16 is this, but if you have n equal to 40, increase the main lobe for the main lobe compensation, increase the number of samples in the Hanning window to 40 instead of 16. So that shrinks the main lobe, so the transition width is reduced. So for a chosen window, you can reduce the ripples on the stop band and in the pass band, but the case of transition width, as the smoothening window increases the main lobe width, so we need to increase the number of samples in that chosen window, that is n equal to 40 in this case, to have the control over this transition band, which is reduced here. So these are the window functions, common window functions, as we said, rectangular, Hanning, Hamming and Blackman used in the design. And the main lobe width increased, we had seen also. The main lobe width is increasing. Increasing main lobe width would cause this transition width, okay, so to increase, right. So that needs to be compensated with the increasing the number of samples in the window. The main lobe width, that is the first main lobe to side lobe level, first peak and the side lobe level first peak, the difference here is minus 13 dB and it is increasing. Also this is called the stop band attenuation, how much stop band attenuation this window can offer. In the design it will be used, say rectangular window can offer the minus 21 dB stop band attenuation. This is a standard, again we use this in the design, minus 44, minus 53, minus 74. So this gives the better stop band attenuation, but the main lobe width is increased. Increasing main lobe width causes the transition widths to increase. So there is a fundamental trade-off between the main lobe width and side lobe amplitude, that is from the window point of view. So if you smoothen the window, main lobe width increases and the side lobe level decreases. The peak side lobe will decreasing and the main lobe width increase, but if we use that will have the impact of ripple reduction. If you smoothen the window, that's good, but it increases the transition width. So to have the transition bandwidth in control, that we need to increase the number of samples used in the window to achieve the longer window can be used to get the transition width which is desired. So to conclude with the filter design, that 1D filter, FIR filter especially, the method used is the common method is the window method, in which choose the desired frequency response and get the inverse DTFT, so that we have the filter coefficients which spreads over minus infinity to plus infinity HD of n, and choose the window function. So multiply these two to have the practical filter, that is the truncated coefficient. So if we take the window function frequency response, so we will have the if you have the rectangular window, that will have the sinc function. So convolving this two in the frequency domain, that is HD and the W, will get the actual filter response, which has the ripple as well as the transition width, depends on the window we choose and the number of samples, and the ripples also is depending on the window function we choose. So the smoother the window, the ripples will be reduced, but the transition width compromise, the trade-off needs to be taken care, that is number of samples in the window function what we choose needs to be longer, so that transition width can be controlled or decreased. So with this we complete the 1D FIR filter design using the window method. With this background, we will proceed with the 2D FIR filter designs and 2D windows also. We will plot the different 2D window functions and see the surface plot of it, and then continue with the design. Thank you.